Welcome to Demystifying Math. In this lesson, we're going to be discussing tension. In this example, we have a 1,500-pound object that will be suspended by two cables. The cables are AB and AD. The tension is really a pulling force of the cable on the object. The cable is going to pull equally on both ends. The system will be considered in equilibrium when the sum of all the forces is zero. If the system is in equilibrium, the horizontal components of the forces will equal each other, and the vertical components of the forces will equal each other. What we want to do is find the tension in AB and the tension in cable AD when the object is steady or when the system is in equilibrium. Keep in mind as we're doing these problems that AB and AD, those lengths represent the lengths of the cables, not the magnitude of the forces. The first thing that we need to do is to find the angles with the horizontal. So if you're looking at the diagram here, we're given that angle ABC is 70. That's this angle here. Angle C is right, so that means that this angle with the horizontal must be 20. So that's angle BAC. On the right triangle, we can do the same thing. This angle D was given as 50. Angle E is right, so this angle A must be 40. So we have those angles with the horizontal. We need that because we're going to write our forces as vectors, and we're going to use those angles to help us do that. So we're going to let the force due to tension through cable AB be represented by TAB, and the magnitude of the force due to tension through cable AB be represented by TAD. Now we know that our opposing forces are going to equal each other if the system is in equilibrium. So we have these two forces that are horizontal and they're opposing forces. So that's going to be the horizontal components of the vectors that represent the force or the tension in the two cables. So the tension in cable AB is the magnitude of the tension times the cosine 20 sine 20. And for the cable AD, it's the magnitude of the tension times the cosine 40 sine 40, using those horizontal angles. Then what we're going to do is take our horizontal components and set them equal to each other. So we have the tension in cable AB times cosine 20 equals the tension in AD cosine 40. Then I just isolated the tension in cable AB. So I have the tension in cable AD cosine 40 over cosine 20. Now we're going to look at the vertical forces. So we have this one vertical force going down, which is the weight of the object, or 1,500 pounds. If the system is in equilibrium, the 1,500-pound weight will just be staying steady and being suspended. It won't be continually moving down. So the opposing forces that's holding it up are the y components of these force vectors, are the cables, the tension in the cables. So what we want to do is figure out what those y components are. So we have for a TAB the sine 20 and for TAD sine 40. So the sum of those two forces must equal the 1,500-pound force pulling down. So we're going to do a little substitution here with what we found on the last slide. So we know that TAB is the force in tension cable AD cosine 40 over cosine 20, and we're going to substitute that in here. And then what we want to do is simplify this a little bit. So I factored out the TADs, and I'm left with cosine 40 sine 20 over cosine 20 and sine 40 here. Now I want to find a common denominator with these two terms, and I'm doing that so I don't have to estimate along the way. I only want to estimate these answers at the last step. So I multiplied the sine 40 by cosine 20 over itself, and then I'm going to bring my two fractions together as one. Now you may recognize this numerator here because this is a sum formula in trig, and we're going to use that to continue to help us simplify this. So if you remember your sum formula, it's cosine u sine b plus sine u cosine b, and that's equal to the sine of the sum of the two angles. So in this case, our u is 40 and our b is 20. So we're going to rewrite this as the sine of 40 plus 20, which simplifies to the sine of 60 over cosine 20, and that makes it really easy for us to solve this. So we're just going to isolate the tension in cable AD by multiplying 1500 by this reciprocal. So we have 1500 cosine 20 over sine 60, and that comes out to about 1627.6 pounds. Okay, so now that we found the tension in cable AD, we're going to try to find the tension in cable AB. So going back to the formula that we had isolated earlier, we're going to replace the tension in AD with what we just found, which is the 1627.6. Then we're going to multiply that by cosine 40 and divide by cosine 20. And we get 1326.8 pounds. So we have the tension in both of the cables. Now what we want to do is check our work. So we're going to go back to the two formulas where we had the opposing horizontal forces first, and we're going to plug in the value that we found for TAB and the value that we found for TAD. So we have 1326.8 cosine 20 for the left side, and I got 1246.8. And on the right side, I got 1627.6 cosine 40, which came out to the same number, so those two sides are equal. You can also go back and check it with the vertical components. So plugging into that formula, we get out about 1500, so it seems to be working for us. So we have solved that. The next thing that we want to do is find out where are the tensions in the two cables equal. So let's go to a dynamic drawing and try to answer this question. Okay, so here we are where we had angle BAC is 20 and angle DAE was 40. And these are our two tensions. Now we want to see where the tensions are equal. So we're going to move our point A along the horizontal and see what happens. So it looks like as I move it to the right, the tension is getting greater on AD. And if I move it to the left, the tension's getting greater on AB. So I want to look to see where the two tensions are equal. So it has to be somewhere in between where I was just at. So let's see what happens. So somewhere in here, looks like when they're both 29 degrees, their tensions are exactly equal. So let's look and see what's happening here. It looks like their cosines are the same and their angles are the same. So let's go back and figure out why that would be true. So we're going to let both of our angles equal angle U. So we're going to let U represent the measure of those two angles. So they're going to be equal. And we're going to go back to the formula that we had for our opposing forces. So the tension in AB cosine U equals the tension in AD cosine U. So we replace the angles with the cosine of U. Well, those are exactly the same. So the cosine of U's can cancel out, and you just get that your tension and your cables are equal. So that's pretty easy to kind of show. But let's answer some more questions as well. When is the tension in the left cable greater than the tension in the right cable? So let's go back to our dynamic drawing and try to see what happens. Okay, so here we are at a point where the two angles are equal, and our tensions are equal, and our cosines are equal. Okay, let's see what happens. As I move the point at A to the right, the angle on the right side gets greater, and so does the tension, and the cosine of the angle gets smaller. So you see that now our cosine is pretty big. Now if we move back over to this way, remember all these numbers are rounded, so if it says 1, it's almost 1. All right, so here, below, um, to the left, we have an angle here on the left side, that's 40, and on this side my angle is 25. Now my tension on the right side is less than the tension on the left, and the cosine is less on the left than it is on the right. So there seems to be an inverse relationship between the tension and the cosine of the angle, and a direct relationship between the tension and the angle measure itself. So let's take a look and see why that's happening. Okay, so going back to our formula, we have the tension times the cosine of the angle, tension times the cosine of the angle on the right side. What I did this time was I created a ratio of the two tensions. So I divided both sides by the tension in cable AD, and then I divided both sides by the cosine of the angle BAC. So what we want to do is figure out where this ratio is greater than 1, so where the cable on the left is greater than the cable on the right. So where the numerator is greater than the denominator, it's going to be greater than 1. So if that's greater than 1, then this side must also be greater than 1. But when we're looking at the cosine and the angle and we're comparing them, the angles are going to be the reciprocal of the cosines. So let's take a look at why. Okay, so here's your cosine graph. As your angle between 0 and 90 increases, the cosine of the angle is coming down. So that's going to be decreasing. So there is an inverse relationship between the angle and the cosine when you're between 0 and 90. And of course, since we're looking at two triangles, our angles are always going to be between 0 and 90. So this will be true for everything between 0 and 90. So we kind of flipped it upside down, and then that relationship is going to be greater than 1, which means that angle BAC is going to be greater than angle DAE, which means that your tension in AB is greater than your tension in AD. So you have that corresponding relationship where as your angle measure increases, your tension increases. Now remember, everything that we did on here, it only had to do with the angle measures. We never took into account the length of the cables. So it's all going to depend on that angle measure. Okay, thank you for tuning in to Demystifying Math.